Hello, this is episode 2 of New Uses for Old Circuits called Sources of Inversion. When I was working on the previous video all about the dual slope generator and using it to process audio, it brought up something that I realized I had been wanting to talk about for quite a while, which is inversion. The Serge features many different modules that can process signals in various ways, but some of them invert the output with respect to the input signal. Why do these inversions occur? Well, usually when you're designing some kind of analog circuit to process a signal, you're using things like op-amps. The op-amp is one of the fundamental components of any electronic circuit. And when using op-amps as part of a larger circuit to do something like filtering or amplification, the op-amp will often invert the signal. Now, typically inverting a signal, especially an audio signal, doesn't really matter. If we listen to our sawtooth wave here and then listen to an inverted version of it, we won't perceive any difference. That goes for more complex signals too. You can invert the waveform of a complete song and you won't hear anything different. Let's prove to our ears that that's the case first. Let's patch the sawtooth into the input of this mixer, which allows us to invert the first channel. And we'll listen to it in the mixer. Here's our original sawtooth wave, positive going, and if we flip the switch, we'll get a negative sawtooth wave. And despite the bit of a blip when we flip the switch, there's no perceivable difference. The sawtooth is an asymmetric signal. When we invert it, we can visually see a difference even if our ears can't tell the difference. Of course, a symmetric signal, such as most of the other typical waveforms, triangles, sines, and squares, well, sometimes the squares are a bit of a funnier shape than a pure square, but if we take the sine, for example, and invert it, there's no difference at all. We can't even visually tell. It's basically the same as just delaying the phase of that signal by 180 degrees. So we'll use the sawtooth to go through the system and diagnose each signal processor and figure out which invert the signals. Some circuits don't invert the signal at all because they don't use an op-amp. Others don't invert the signal because they use a second op-amp to re-invert the signal. That's purely a design choice. Sometimes it's worth the money to have a processor preserve the inversion of the signal. Other times, however, it's just another expense that isn't all that necessary because your ears don't tell the difference. When we move on to the Paperface circuits, we'll see that a lot of those modules invert the signal purely for price considerations. You already have a handful of op-amps being used to do what the module is supposed to do, and adding another op-amp just to reinvert the signal is another cost. Op-amps typically come in packages of 1, 2, or 4. Often you'll see things using a Texas Instruments TL071, which is a chip that contains 1 op-amp, or a TL072, which contains 2, or, even more common, a TL074, which contains 4 separate op-amps. If you're already using a TL074 in your module to do a handful of op-amp things, then at some point you'll run out of op-amps, and adding a whole extra chip just to invert the signal is a bit of a burdensome extra cost. But so if our ears don't care whether the signal is inverted or not, why am I doing this video? Why do we care whether the signal is inverted? Well, when we start looking at feedback in the system, it starts to be really important whether or not a processor is inverting the signal or not. If you're adding 2 signals together and one is inverted with respect to the other, you'll start to get a lot of destructive interference. So when you're designing big feedback paths on the system, knowing whether or not a module is inverting the signal can be a really useful thing to know. So let's create a little map of the Serge synthesizer to understand where these inversions occur. Again, we'll use the sawtooth wave as a reference signal because it's asymmetric, so we can easily tell whether or not it's inverted. Our original is a positive going sawtooth, and the inverted version will be a negative going sawtooth. Let's just start with the stereo mixer. What happens if we patch the sawtooth directly into the mixer? Does the mixer output invert the sawtooth or not? Patching the sawtooth to the mixer input channel and monitoring the mixer output, once we raise the level, we see that in fact the output of the mixer is inverted with respect to the input. That's really good to know because typically the mixer is at the output of our chain. So odds are if you've been working on things in the Serge synthesizer, you've already been listening to an inverted version of what you were working on anyway and you didn't really notice. Next, let's look at the variable Q filter. If we put the sawtooth in our input and open the filter all the way and monitor the output, let's turn the resonance down, we'll see that the low pass output at least is not inverted. It's positive going. If we take the high pass output and open the filter the other way, again, we see that the sawtooth is positive going. It has a little bit of filtering applied, but that's okay. We still see that it's not inverted with respect to its input. Let's look at the notch output. The notch output actually is negative going. Of course, as we sweep the notch, we get all sorts of things, but we can see that we're getting a negative going sawtooth instead of a positive going one. So the notch inverts the input. What about the bandpass output? Well, there's no fully open for the bandpass, so it's hard to really see our original signal. We could say that maybe it's positive going, but we're not really sure because we can't get a full sawtooth wave. There's no sort of bypass setting for the bandpass filter. That said, the variable Q is a really interesting module because its 4 outputs are phase inverted. That is a really useful tool and something we'll talk about in a later video. Let's move on to the variable slope filter. We'll go into an input and just like the variable Q, we'll look at the low pass output and we see our output is inverted. The sawtooth is going down. What about for the high pass filter? Again, output is inverted. The sawtooth is going down. The bandpass we won't even look at for the same reasons that we didn't really look at it in the variable Q. What about the variable bandwidth filter? If we go to the input and monitor the low pass output and fully open, we see that we get our positive going sawtooth. So this output is not inverted. What about the second low pass filter? Again, not inverted. High pass filter, still positive going, not inverted. What if we look at the variable bandwidth output? It's a bandpass filter, but we can widen it to maybe see what we're working with. But it's still a bit hard to say whether the output is inverted or not. But I would say it looks like it's negative going. I don't know. But with bandpass filters, again, because there's no fully open setting, it's really hard to tell and almost kind of meaningless whether or not it's being inverted or not. Let's look at the resonant equalizer. If we go to the input and take the output, well, we have to change our settings here so we have something of a transparent signal. But we can see that in general, we've got our positive going sawtooth wave. It's a bit mangled, but in general, our sawtooth wave is positive going, so not inverted. What about the comb filter outputs? Well, they are a bit kookier than the main output, but we could say they're not inverted? I don't know. Don't really know. What about the individual band outputs? It's going to be hard to tell, kind of like the bandpass filter. We can go around and look at them, but it's hard to say, hard to really say whether or not it's inverted or not because, again, there's no clean response. Down here, we're getting basically sine waves anyway. Next, let's look at one of my go-to sources for inversion, which is the top section of the wave multiplier. I kind of spoiled the ending, but yes, the top section of the wave multiplier inverts our signal. What was a positive sawtooth is now going downwards. The middle section of the wave multiplier also inverts our signal. Set to low, we get more or less our input signal, and we can see that it's a negative going sawtooth wave instead of a positive one. How about the bottom section of the wave multiplier, the rectifier? If we go to the input and output, we'll see that we actually get our positive going sawtooth wave. So very interesting. So the top two parts of the wave multipliers invert the signal, whereas the bottom one does not. As I mentioned earlier, this video is in part driven by the fact that in the last video I was making on the dual slope generator, we were looking at processing audio and using the outputs. Well, the dual slope generator is a very interesting case. We take our sawtooth and patch to the input, and if we monitor the unipolar out, we get our sawtooth wave positive going. But if we monitor the bipolar output, we see our sawtooth is now negative going, and it's also now centered around 0 volts. Again, our positive going sawtooth, which is unipolar, going from 0 volts up to 5, and our bipolar version, which is inverted with respect to the input. This can be a really useful thing to know when you're playing with the slope generator. The smooth generator in the GTO here, let's check that, and we get not inverted. We get our positive going sawtooth wave. The triple wave shaper is a bit of a special case because, again, there's no real transparent, fully open version. As we adjust the wave shaping, the triple wave shaper is a sine to saw shaper. And so the outputs we're getting are all kind of sinusoidal because that's kind of the whole point of the module. So it's really hard to tell whether or not it's inverting the signal or not. What if we cascade two of them together? Again, really hard to say. I can tell you that the triple wave shaper is basically using a single LM3900 chip, and so I suspect that maybe there's some inversion going on, but because the output is symmetric instead of the asymmetric sawtooth wave that we're plugging in, we can't see and we can't say for sure. Which is also to say that in this case, since the output is symmetric, it kind of doesn't really matter. Let's check the ring modulator. Put the sawtooth in, monitor the output, and we get a negative going sawtooth. So the output of the ring modulator is inverting the input. What about the active processor, which is a crossfader module? Let's look at the output and go into the input, and we'll see we get our positive going sawtooth. What if we go into input 2 and crossfade over to that? We get our positive going sawtooth. Now, the interesting thing about this design of the active processor is we have this switch. If we switch out of normal mode, then we don't see anything different at first, but if we go to signal 1, of which there's nothing plugged in, we'll see we get actually a inverted version of whatever is in input 2 as signal 1. This is how you can use the active processor as a ring modulator. This is because ring modulation multiplies two bipolar signals together. The key difference of ring modulation as opposed to amplitude modulation has to do with the fact that the signal goes negative and you get destructive interference which takes out the carrier signal. But that's a topic for yet another video. How about the peak and trough here? Go to the input, and the output we get a positive going sawtooth. For the trough, we get a positive going sawtooth. No inversion is going on here. Last but not least, the crossfader. Go into the input, monitor the output, go into channel 1's input, and we see our positive going sawtooth. So that wraps it up for this side of the system. Let's move on to the Paperface circuits. Okay, this video is already probably too long for what it is, but let's just forge ahead and go through the Paperface circuits quickly. The positive slew we can see gives our sawtooth positive going, so it is uninverted. The negative slew is the same. We can see that it's already applying a bit of negative slew at that falling edge, which we can obviously lengthen like we saw in the previous video. Recall that the positive slew and negative slew are the precedents of the dual slope generator, and they're basically separate versions of the rise and fall portions of the slope generator. Next, we'll jump over to the old SSG, the original SSG, and we'll look at the smooth output, which It's giving us a much more triangular version because the SSG doesn't run at the high rates that the GTO does, so it's applying a bit of slew whether we like it or not to our audio rate signal. We can judge for sure if we turn down the rate of our oscillator. Yeah, so it's positive going, so that this is not an inverted version of the input. The phaser is going to be a bit of a weird one because we have all these different phase outputs. So kind of like the bandpass filter, it's going to be a little hard. Well, yeah, it's going to be really hard to say whether this is inverted or not. Whether we look at either output, it's really hard to say. So let's chalk that up to doesn't matter. Let's go into the gate, which is a VCA. If we go into the DC input and take the output, we see that our signal is positive going. It's quite small. So if we just zoom in a bit, yeah, we can see that we get our positive going sawtooth. Whereas if we go into the AC input, we get a negative going sawtooth. This is one of the fun things about the gate module because these two inputs are inverted with respect to each other. Also, the two control inputs, the linear and the log, despite having different responses, they also are inverted for each other. I'll do a video on the gate because I do think it's one of the most underrated modules in the Serge system for how interesting it is. Let's look at the ring modulator, which is just kind of a different arrangement of the same things that are on the gate module. If we go into the X input, we'll see that our output is positive going, so not inverted. The filter, the original Serge filter, let's look at the low pass output and open the filter all the way, and we get our positive going, so not inverted. Let's look at the high pass, open it up the other way, again, positive going, not inverted. The mixer, I know for sure definitely inverts. If we look at the output and go into the input, we can see, yes, our output is inverted. The mixer is a dead simple circuit. There is in fact just one op amp for each mixer. On this one, I believe I'm using a TL071. And so that's just a single op amp that's doing this. And if we wanted the outputs of the mixer to preserve the original symmetry of the signal to not invert it, then we'd have to double the amount of op amps in the whole circuit. So for such a simple circuit, and really it is dead simple, you should take a look at it because it's pretty amusing. It's really just an op amp for each. Yeah, we don't want to double the cost of this thing just to invert the output. So yes, the output of the mixer is inverted. Triple wave shaper is pretty much the same as the other one. We've already done it. Peak and trough, same thing. Peak and trough are really just a collection of diodes and a couple transistors. So yeah, that preserves that doesn't invert the signal. Comparator, again, a special case because the output's always going to be square. So it kind of doesn't really matter whether or not, you can't really say whether it's inverted or not. The triple comparator uses a quad op amp. It uses the LM3900, which is used in most Serge circuits. And so it has so it's using 3 of those op amps. And so if we were to invert any of them anyway, we'd have to get 2 more op amps in there. But anyway, the output is always square. So whether or not the output inverts is kind of a meaningless question anyway. The dual processor inverts the output as it should because it's a bipolar version of the dual mixer. And so you certainly would want it to invert the signal. So if we have the signal going positive, yes, we get our positive going sawtooth. And as we go down, we get our kind of mirrored over the x-axis here, negative going sawtooth. So it's funny to really just play with the mirroring attenuversion. And that's about it. The only other thing to check is the reverb. And the reverb, yep, doesn't invert the signal, keeps our positive going sawtooth. So that's it. This video was probably too long, but we've gone through everything that at least is in my Serge system and checked for inversion or non-inversion of outputs relative to the inputs. This is just a good thing to know, and I hope this video was helpful in some way.